Okay, let's do another problem here involving calculation of an entropy change for an ideal gas. We have an air compressor here. Don't worry the fact that an air compressor is an open flow device. We're simply interested in calculating a change in entropy, so don't worry too much about this. We have an air compressor. The inlet is located at location 1, and the outlet is located at location 2. So at location 1, the air has a temperature T1 and a pressure P1. And at location 2, the outlet, the air has a temperature T2 and P2. Now the air compressor does work on the air, compressor work to pressurize the air and heat it up as a result. So the inlet temperature is 290 degrees Kelvin, basically room temperature. And the pressure is approximately an atmosphere, 96 kPa at the inlet. At the outlet, the air temperature is 600 degrees Kelvin and the pressure is 10 megapascals, which is approximately 10 atmospheres. So we have an air compressor here. Pressure has gone up, temperature has gone up between the inlet and the outlet. I want to find the change in entropy, specific entropy, between the inlet and the outlet of the device. How much has the air per unit mass change in entropy as it flows through the compressor? What's delta S from 1 to 2 or S2 minus S1? Okay? So what's the change in entropy of the air as it flows through the compressor? Well, this doesn't say anything about IGB, so I think I better assume ideal gas behavior. So assumptions. So IGB. So for the delta S equation, I have two sets to choose from. One for constant specific heat, one for variable specific heat. It doesn't say anything about constant specific heat here, so I guess I better assume variable specific heat. It wants the exact change in entropy. So this is variable CP, CV, variable specific heat. Okay, let's write the equation for delta S for an ideal gas. So delta S, this is specific entropy change. And then I got two versions for variable specific heat. I've got the general one, CV dt over T plus R ln V2 over V1. I have that. I don't know how I'm going to actually evaluate the integral given that specific heat is variable. Or I have the version involving enthalpy and Cp and S naught. So I also have this version, S naught evaluated at T2 minus S naught evaluated at T1. These are lowercase s's. I don't know why they're so big. So we have S naught minus R ln P2 over P1. So I have these two equations here. I can use either one. Clearly, the second one is most useful. The S naughts are in tables, IGB tables, and I'm given the initial and the final pressure. So I know the pressures. The gas constant is pretty easy to get. I can get that for air. And these S naughts, well, I can look them up on the table, but I also know T1 and T2. So I can look up these S naughts evaluated at temperature T1 and T2. So calculating delta S from the inlet to the outlet is quite easy if I use the second version. Okay, here. So let me erase this. And I'm going to write the second version. We're not interested in the first version. It's not helpful. So I have delta S from 1 to 2 is equal to S naught evaluated at T2 minus S naught evaluated at T1 minus R for air ln P2 over P1. Now let's figure out what some of this stuff is. Let's go look up in a table S naught evaluated at T2, what's our temperature at the outlet? That is 600 degrees Kelvin, so it's hot at the outlet. Okay, so let's look up S naught evaluated at 600 degrees Kelvin. Let's see here. So IGB, ideal gas properties, air. Temperature, HU S naught, 600 degrees. 2.409, 2.409, 2.409. And that is kilojoules per kilogram degree in Kelvin. Okay, so that's from table, what, B11? B11, IGB air tables. B11. Let's also look up S naught evaluated at T1, which is 290 degrees Kelvin. Let's go to the same table. Let's go to the same table. $290, 1.668, 1.668. .668 kilojoule per kilogram degree in Kelvin. Okay. Check, check. We have the pressures. R for air, what, 0.28 something. I guess I can divide the R universal divided by the molecular weight. Let's see here. I never remember these things. Let's see, R for air, 0.287, I think it is. Just better make sure. 0.287, 8.314 divided by 28.97. 0.287, yes. Okay, kilojoule per kilogram degree in Kelvin. All right, so 2.409 kilojoule per kilogram degree in Kelvin minus 1.668. Same thing, minus 0.287, same unit. Ln, okay, what's the pressures? Pressure at the outlet is 1 megapascal. So 1 megapascal, and I got to convert that into kilopascals. That's what P1 is. So there's 1,000 kPa, oops, not 100, 1,000 per 1 megapascal. Okay. And then that is getting divided by the inlet pressure, P1, which is 96 kPa. So what's delta S? What is delta S? All right, let's crank this out here. So 1,000. Sorry, natural log 1,000 divided by 96, and that's multiplied by 0.287, and I'm going to subtract off 2.409, 0.668, and I get 0.068 kilojoules per kilogram degree in Kelvin. So the change in entropy from the inlet to the outlet. The change in specific entropy from the inlet to the outlet of our air compressor, delta S1 to 2, which is S2 minus S1, that's equal to 0.068 kilojoule per kilogram degree in Kelvin, okay? By the way, I haven't said much about it, but if, as the drawing indicates, this is an adiabatic turbine, I put some insulation around it. The fact that specific entropy is greater at the outlet than the inlet means that there's some entropy being generated inside. There's no heat transfer going on, so there's no entropy transfer from the outside, the environment. So that means any change in specific entropy from the inlet to the outlet must be due to irreversibilities. So this, by the way, if it's an adiabatic compressor, it's actually an irreversible adiabatic compressor. Note, if adiabatic, in other words, Q dot is equal to 0, no heat transfer, then this is definitely an irreversible compressor. Why? Because S2 is greater than S1, okay? We'll talk about this a little bit more when we get into open systems in the next lecture. Open systems in the next lecture.